We will wait for 1 more minute. 1 more minute. He asked me to introduce. So, well, if he's not here, hey, why don't well, JD will have to be here for that. Let's follow the German tradition of starting at 5 minutes past hour. Okay. So everything is ready, no? Yes. Okay, so I'm sorry, I apologize. I was a bit late for coming in. So thank you all for coming to this week's Wednesday colloquium. And it's actually a pleasure to have one of our own students come back here and give a colloquium in AG66. I'm sure you have good memories of this lecture theater, Gulab. So, and when Professor Gopakumar told me that there is a possibility of you coming here, so we are very happy, and the fact that we are proud that you are associated with new discoveries as it is coming out from our own country. So without further delay, I would like Professor Gopakumar to introduce formally Professor Gulab Divangan. Yeah. Thank you, JD. So it's a pleasure to reintroduce to many of you Gulab Chandevangan. He was a professor in Ayuka. He's, as JD mentioned, he's one of our own. So Gulab came to TIFR some 30 years ago and graduated around 20 plus years ago, and then went to Carnegie Mellon. He actually worked with KP Singh. You are familiar, many of you are familiar with. His interests are, there's a lot of interest in X-ray astronomy, but on active galactic nuclei, that's he's going to talk about today. Very exciting developments. And then X-ray binaries. He's interested, he actually instrumental in developing science pipelines, both for the SXT and UVIT, which are parts of AstroSat, India's own satellite for astronomy. And he has been in Ayuka for many years now, and he's a professor there, as I mentioned. And we are all excited about recent developments, especially on something called quasi-periodic eruptions. That's one of the topics Gulab will be talking about. Without any further ado, to Gulab. Thank you.
Thank you, Gopu. Thank you, JD, for this generous welcome and the introduction. I am really very happy to come here. Visiting here for me is walking down the memory lane with some nostalgia from our good old PhD days. It's a bit like opening one of my old textbook and finding what I crammed in on those days. And you also find, okay, some of the things probably I couldn't do it, but that's the kind of thing. But seriously, it is delightful to be here among you, among the familiar faces, and the place, of course. So today I'm going to share some of the recent findings in the study of galactic nuclei. So the galactic nuclei, active galactic nuclei, of course, are being studied for a long time. But recently, with large surveys in various web bands, there are new developments which I will try to convey to you. Some studies have suggested that there are about 2 trillion galaxies in our universe. And these galaxies actually come in different kinds of morphologies. And if you look at, I mean, there will be spiral galaxies, there will be elliptical galaxies, there will be irregular galaxies also. And if you look at the light profile of some of these galaxies, generally these are smoothly varying apart from some of the structures like spiral arms, etc. Okay, most of these galaxies are like this smooth light profile. But then a small subset, 10% of all galaxies, show very, very bright nucleus at the galaxy centers, of course, like this one. And telescopes do not resolve these very bright nuclei. They look like very point-like or stellar-like objects at the centers of these galaxies. Sometimes we do not even see the host galaxy. We see very, very bright nucleus only. So these objects, these bright nuclei are called the active galactic nuclei because the nuclei are very, very active. They actually represent some source or some energy source other than the stars. In normal galaxies, almost all the light actually is from the stars. In these cases, the very luminosity from the very bright nuclei represents some energy source which is not from the stars. And these only the point source in the nucleus can dominate the total light from the entire galaxy. And this is a huge, huge luminous power. And these AGNs, or these active galactic nuclei, are now, of course, known as the most luminous, continuously emitting objects in the universe. Of course, we have objects which can actually exceed the luminosity of these AGNs, for example, the gamma ray bursts, etc. But those are for very, very short duration. And here we have the most luminous objects which are emitting continuously. So how do we find the AGNs? First of all, there are presence of very, very bright nucleus at the center. That's one short signature, not only in the optical, in the ultraviolet. For example, this is the far ultraviolet image actually taken with AstroSat. And this is the X-ray image taken with Chandra X-ray telescope. Again, you see very bright nucleus. But there are other very important signatures. For example, some of these active galactic nuclei eject relativistic jets from the very center of these galaxies. And these can be observed primarily in the radio, but also in the optical as well as in the X-rays in some cases. So there are a variety of observational signatures or different observational signatures one can use. To summarize, these AGNs have very large luminosity, something like 10 to the power 42 to 48 ergs per second. That's a huge, and this is actually comparable to the luminosity of 10 to the power 9 suns, a billion suns emitting in the central region only, or more than that. They are, because they're not resolved with our telescope, they're very, very compact. Size is less than about a parsec or a light year. They also emit over broad electromagnetic band. In fact, over almost entire electromagnetic band from radio to optical X-rays, gamma rays, etc. This is very unlike the stars. Because stars having a temperature of few thousand Kelvin to tens of thousands of Kelvin, their emission is generally confined in the near infrared, optical, or the ultraviolet emission. They have some of the AGNs show very strong emission lines in the optical and UV, and we will see some of these spectrum, their spectra. They also have very strong X-ray emission. Some of them also emit in gamma rays as well. And they are also strongly variable. And one aspect of study this talk is on extreme variability of some of these objects. And as I mentioned, they have some of them only about 10 to 20% have jets and lobes in so-called radio-loud active galactic nuclei. And these jets can originate from the nuclear region, can move to parsec, kiloparsec, and sometimes even megaparsec scales. They can be really, really joint structures. But today's my talk is I'm going to focus on the central engine or the nuclear region of these things. So what powers these active galactic nuclei? How does the huge luminosity actually arise from these objects? So to find that out, one can use very, very basic physics. For example, the huge luminosity we observe, that actually implies a huge mass. And fast time variability implies compact sizes. How do we get this information? So very simply, if any object cannot emit arbitrarily large luminosity, because when there is a large luminosity, then the photons interact with the surrounding material, and then due to the radiation pressure, and that radiation pressure force actually can throw out the material if they are not balanced by the gravitational force. So one can, every object can have a maximum possible luminosity, which we call the Eddington luminosity, and that you can simply obtain by balancing the radiation pressure force, which is outward, and the gravitational force, which is inward. And that turns out to be about 10 to the power 38 ergs per second per one solar mass object. And here, in the case of AGNs, we have huge luminosity, as I mentioned, 10 to the power, about 10 to the power 45 ergs per second or so. So therefore, this very simple idea provides us the AGNs must have masses of the order of million, or 10 million, or even billion solar masses. So the huge luminosity means huge masses. Now, of course, there are sophisticated techniques, very advanced techniques, which and we measure very accurate masses, and these masses range from something like 10 to the power 5 to 10 to the power 10 solar mass. The other very important characteristic is the variability. For example, this is the X-ray light curve. X-ray flux is a function of time, and you see very fast variability. You look at the scale here; it's in thousands of seconds. So these AGNs can actually vary on very short time scales, on scales of an hour or so. And what is the significance of this? Because if how do you produce the variability? And this variability is by a factor of 2 or so. If you are talking of
Just a quick question.
yes.
When you said luminosity, you're showing some spectral range now for the X-rays, but is that luminosity is divided all the spectrum? It's a summation of all.
Certainly all the bands over. But even if you look at in the optical ultraviolet, this is already very high.
Is that?
Yes,
So
yes.
or the scale variability for what kind of mass?
10 to the power 6, 10 to the power 7 solar kind of masses. It is, yes, it's less, yeah, it's kind of a light travel time. So this is what I'm going to discuss. So because in this 1 hour fevers time scale, there is a change of almost a factor of 2 or so. So something like this can happen unless cannot happen unless the entire emitting region is participating in this kind of a variability process. So you can imagine, okay, there was probably a disturbance at the central, and this disturbance started causing the variability and travel outward, so that the entire emitting region is participating in this variability event, and that is the requirement. Because any disturbance or anything cannot travel faster than the speed of light, so it has to be the size therefore has to be less than the speed of light times less or equal to the speed of light times the observed variability time scale. So in this case, if you apply this 1 hour, then the side scale turns out to be 10 to the power minus 5 parsec, or about 10 to the power 13 centimeter. And this is comparable to the Earth-Sun distance. So the huge luminosity is coming from very, very compact region. So now from these basic observations, we can come up with the following conclusion. First of all, this high luminosities tells us through the Eddington limit, this huge mass, and this huge mass must be confined in a very, very compact size, which we are inferring from the time variability. So some billion or millions or billions solar mass object is confined in a size which is less than the solar size of the solar system. In physics, we do not know anything other than black holes. So therefore, we say that there is a supermassive black hole at the centers of galaxies. And then when there is a supermassive black hole, of course, it influences the surrounding medium due to gravity. And then this results in the accretion of material from the faraway regions to toward the central black hole, toward the central black hole. And due to this process, the material which is being accreted loses gravitational energy, and that energy is gets converted into heat and radiation, and that is what produces the huge luminosity. So to remember the basic physical picture of AGN, so there is a central supermassive black hole from 10 to the power 5 to 10 to the power 10 solar mass. When you think of the size scale, you can think of a Schwarzschild radius, which is essentially the event horizon for a non-rotating black hole, and from within which the event horizon, nothing can escape, including the light. They have large luminosity, as we have saw. They are powered by accretion, and with a typical efficiency, one can take is about 10% or so. So if an object emitting at the Eddington at a luminosity of 10 with the Eddington luminosity, that will require 2 solar mass per year of accretion rate if the black hole is about 10 to the power 8 solar mass. So that's typically the accretion rate one can think of is a solar mass per year. That's the kind of the situation required here.
How do you know the ether is one?
One can basically calculate, even from simple physics, you can take a proton, which is going closer and closer, and you can find out, okay, what is the gravitational energy release, how does the gravitational potential energy decreases, and then find out. You convert that into, for example, GMP divided by R, and take the inner radius for a Schwarzschild black hole of 6 RG, and you convert that, you'll get about 10% to.
Just the R.
Yeah. So yeah, nothing was in that. Yeah, so if you use GR, then this efficiency can go up to 43% or so.
Yeah.
So that can be because for the curve, maximally rotating curved black hole, the inner radius is strings.
But that's the maximum energy.
Yes.
It's much lower than that.
Yes. Yes. So this could be of the order of 10%. That is why I'm quoting this. Yes. Yes. That's right. Okay. The accretion of matter, when you think of it, because the matter which is being accreted has a certain angular momentum, so it cannot directly fall into the black hole. It has actually to orbit around the supermassive black hole, and the conservation of angular momentum actually forms a disk, which we call the accretion disk. And the theory of this accretion disk was first provided by Sakura and Sunya a long time back in 1973. What they told us that the temperature of the accretion disk is not really constant. It varies as a function of the radius to the power minus 3/4. So what that means is that the temperature is highest close to the black hole, and then it decreases. In fact, very close to the Schwarzschild radius, the temperature is about 6 × 10⁵ Kelvin for a black hole of mass 100 million solar mass. Okay, so you are once you have the temperature, you can find out. You can quickly imagine. Okay, where does the emission should peak? Using the Wien's law, because these are optically thick medium. So in order to find out what kind of spectrum these accretion disks actually emit, one can simply assume, one can simply divide the accretion disk in a large number of rings and attach a temperature to each of these rings with this prescription. Okay, and then calculate the black body spectrum from each of the rings, and then sum all these black bodies, and then you will have an accretion disk spectrum. Do we observe such a accretion disk spectrum? Yes, of course, there are some complications, but we do see observations. For example, this is the spectral energy distribution of AGNs from infrared to X-rays. And you look at this component, which is the strongest component, and we call this component as the big blue bump, because it comes in the blue region of the spectrum. And this is this particular big blue bump is actually well described by the emission from the accretion disk, which is like a multicolor black body emission. Okay, and now let's focus on this intrinsic AGN emission. One of these is the accretion disk component, the big blue component, and then above this component, because the big blue bump can go down to very softest X-rays. Above this component, of course, there is an X-ray continuum, and this X-ray emission is dominated primarily by a power law which cuts off at hundreds of kilo electron volt. So how does this X-ray power law arises? Because these two components are the primary AGN components arising from the very central region. Other parts like the infrared emission, etc., are all reprocessed. So you can simply assume we have a supermassive black hole and there is an accretion disk around it. And then what we need to explain is this, the X-ray emission is something called hot corona. So it essentially consists of energetic electrons because the temperature is very high, something like 10 to the power 9, even 10 to the power 9 Kelvin or so. So then what happens, this accretion disk, the temperature of the accretion disk is something like 100,000 Kelvin. So it is emitting the optical photons, ultraviolet photons, and these photons are interacting with the energetic electrons in the corona with this kind of temperature. So what is going to happen? Inverse Compton scattering. So now because this material, because of course there are a large number of this energetic electrons with some optical depth. So these photons have to undergo repeated inverse Compton scattering. And that repeated inverse Compton scattering actually produces this kind of a power law. So another way to understand this basic thing is one can assume, okay, there is an initial black body, approximately black body emission, and each step in the inverse Compton scattering, you take a fraction tau of this optical depth, and this goes to inverse Compton scattering. So therefore, it's increasing. Overall energy increases. In the next step, the same thing is repeated until the photon energies become comparable to the temperature of this electron corona. And beyond that, of course, photon energies you cannot increase by inverse Compton scattering. So therefore, there is a cutoff. So that is how you generate a power law X-ray continuum with a high energy cutoff at around few hundred kilo electron volt. So of course, that is the primary emission, the accretion disk emission, and the broadband X-ray power law cutting up at a few hundred keV. But there are many more components in AGNs, and with a study at over multi-wavelength over a long period of time, what people have realized is that the central engines or the central region of this the galaxies which are active is something like this. So first of all, we have a galaxy which scales up 10 to 100 kiloparsec or so. In the very central region, we have the supermassive black hole, and it accretes and forms an accretion disk around it. And then there is somewhere this hot corona, something like here, base of the jet. It could be slightly bigger also. We do not clearly understand what exactly is the geometry of this accretion disk and hot corona at the moment. But one possible geometry is this. You have an accretion disk and a compact corona in the symmetrical axis. When you go further away,
you need this hot corona to explain the upscattered photons.
Yes, we need the hot corona to explain the X-ray radiation. Yes. So the size scale for this accretion disk could be a fraction of light years. Okay, you go beyond that, then there is something called a torus. This torus was initially introduced to unify different classes of AGNs. I'll come to that. But within in the inner regions, there is something called the broad line region, or some kinds of clouds which are actually emitting emission lines, which are really, really broad. We'll come to that also. And then at larger scale, of course, there can be jets in some of the AGNs which are launched from the very central region, from the inner regions of this accretion disk, and in the symmetrical direction, and much larger scales compared to this torus. There are other kinds of clouds which are also emitting some kind of line emission, but they are much further away, and they actually are emitting narrow emission lines. This entire picture, this particular picture, this torus covering this broad line region, but not covering the narrow line region, etc., were introduced to explain the width of the emission lines, as well as to unify different classes of these AGNs. For example, if you look at the optical spectrum of AGNs, they come in different varieties. One of them actually shows very strong continuum, blue rising towards blueward. Okay. On top of that, you see the emission lines, and you see the two sets of emission lines. One set of emission lines, particularly from the permitted lines, they're broad. The widths, the velocity width is something like 5,000 kilometers per second. So they are actually going around, moving with speed up to 5,000 kilometers per second. The other sets of emission lines, usually forbidden lines, they are very, very narrow. And the velocity width of those lines is only about 500 kilometers per second. So these whenever we observe this broad emission lines along with this narrow emission lines, we call them as type 1 AGN. This is a purely observational classification. And in some of the other AGNs, we only see this narrow emission lines, then we call them type 2 AGNs. And both types are actually unified by introducing this torus. For example, if we are looking, let's say, if our line of sight does not pass through the torus, and then we have a direct view of the innermost regions. So we have a direct view of the accretion disk, hot corona, and the broad line regions. So therefore, we see the broad emission lines in the optical spectrum. While in the case of type 2 Seyferts, our line of sight passes through this torus made up of cold, dust, and gas. So we do not have a direct view because this medium, this torus, actually obscures the entire central region. But what we can see, because we can see only the narrow the emission from the narrow line region, therefore we only see the narrow emission lines in this type 2. But these are the models came up quite a long time back, but there are new observations which kind of raise questions, which we will see that. So the variability, the variability is one of the generic properties of AGNs. So you look at any, whether it's optical, ultraviolet, X-ray, etc., you find that AGNs actually vary quite a lot. And this variability, for typical variability of a factor of by 2 or so, is very, very common. It's you observe in many of these AGNs. But recently, this is the light curve. Okay, so this is the light curve of one of these AGN, NGC 5548, observed with the NASA Swift X-ray telescope in the ultraviolet band. Okay, this is one typical variable of a typical AGN. But recently, there are very interesting discoveries in some AGNs, very, very extreme variability by factors of 10 to 100 increase in flux has been discovered. So and when their flux changes by these huge factors, they change their appearance also. And this is what I'm going to discuss one of them. So such AGNs are called changing look AGNs. The others are called quasi-periodic eruptions. Then there are also nuclei of some galaxies, which are apparently normal all the time. But then they go through extreme changes, and where the flux actually was very, very low or almost zero, you can say, due to the AGN or no AGN. Then they increase by huge factors. So these are the tidal dispersion events, and I will discuss more about these type of objects. So what are these changing look AGNs? They exhibit dramatic changes in their observational properties, flux, spectrum, etc., on time scales of months to years. What really happens is that this is the light curve, optical light curve over 15 years for one of the AGN here. Okay. And you see here the flux was very, very low, and then it increased by almost by an order of magnitude over some 5 years time scale or so. And then it has remained like this. And when this flux changes by an order of magnitude or so, what happens to the spectrum? When the flux is very, very low, the spectrum you see here shows only narrow emission lines, the continuum is weak, and what you see is only narrow emission lines. While when it goes into a high flux state, the spectrum changes completely. Now we have broad emission lines here, broad emission lines, as well as up to the narrow emission lines. The continuum becomes much, much bluer. And if you subtract the low flux spectrum from here to the high flux spectrum from here, what you get is the spectrum which is rising fast towards the blue web. So this is here, essentially these objects, these changing look objects are essentially transitioning from type 2 to type 1 or vice versa. That is why they are named as changing look AGNs. So
Periodic or
this
no?
is not periodic.
It's
So
non-periodic.
it is, so far we don't know these are not periodic because they are several months or years time scale. But there are few AGNs which have shown multiple transitions from type 1 and type 2. There we do not see the period. Okay. What causes this kind of changes? So in some AGNs, at least in few of the changing look AGNs, we know that there are clear changes in the obscuration column. So when we are looking towards the AGN, there is always some kind of a material which is obscuring, and there is there are observations where this obscuration column or the amount of obscuration is changing quite a lot. And for example, what happens if the obscuration changes? For example, this has been inferred from X-ray observation, but this is to explain how does the absorption changes the spectrum. So in X-ray astronomy, what we measure is individual photons. So we measure our spectrum in terms of photon flux as a function of energy. And for example, this is a power law. So because this is a y-axis is a log scale and x-axis is also log scale. So any linear line here is actually a power law spectrum. Okay. Now we introduce some kind of absorption, some kind of obscuration, and that essentially to use this factor e to the power minus tau. Tau is optical depth, product of this cross section and the obscuration column. And this here it is abundance weighted absorption cross section. So what happens? So if you have a very low absorption column, like 21% centimeter square or so, then you have the soft X-ray excess, you can observe very well, and then at the lowest energies, it cuts off. And when you increase this obscuration column, then the spectrum starts cutting off at higher and higher energies. For example, when it becomes the obscuration column is something like 24% centimeter square, then the emission is cuts off at around 10 kilo electron volt.
So Gulab, in the plot, we see some kind of jump somewhere. I mean, it's coming and then, so what are those supposed to be?
These are very important signatures of this absorption because by the neutral material. And whenever there is a jump, that is the absorption age due to different elements. For example, this one is due to iron. This one is due to carbon, and here there is one due to oxygen. These are the most abundant elements. And this is a kind of, if you have good resolution spectrum, these are the sure short signature for identifying such absorption. Okay, so this absorption, change in the absorption can change the appearance. One such AGN is NGC 4151. And here is the long-term flux variability of this particular AGN. So in 1995, the flux was highest, and then it reduced to quite low values, more than factor of 2 or 3, about factor of 3 or so. And here, at least a lot of this variability is caused by changes in the obscuration column. Here is the X-ray spectrum. Here you see the hard X-rays, because hard X-rays are not really that much affected by absorption, because your photoelectric absorption cross-section is strongly depends on the energy. So at the low energies or at soft X-rays, photoelectric absorption cross-section is high. So therefore, you see this absorption. And this change in 1 to 6 keV is essentially due to changes in the absorption here. And any emission below 1 keV it's actually coming from far away region where this obscuration is not there. Because if there is an X-ray, okay, so if there is X-ray obscuration, then there must be some kind of a UV obscuration also. Of course, the X-ray emitting region and the UV emitting regions are different. So we decided to look this particular AGN with AstroSat, utilizing its multi-wavelength capability. I'm sure you all know about AstroSat, but yes.
Yeah, this was the nature of this obscuration, or what is it?
That's I'll come to that. That is.
So it's not torus, right? It's some dense hot gas, or
I'll come to that. So
Okay.
I'll come to that. So in order to investigate more on what exactly is the causing this obscuration and what is the connection between UV obscurer and the X-ray obscurer, we performed this multi-wavelength observation with AstroSat, utilizing its multi-wavelength capability. I don't need to tell you about AstroSat, just for the sake of completeness. AstroSat has 4 different co-aligned instruments working from the near ultraviolet, even visible near ultraviolet far UV, to soft X-rays, then hard X-rays through various instruments. And the 3 X-ray instruments here, the SXT, LEX-PC, and CZTI were actually developed here. So I'm sure you know very well. So these co-aligned instruments, they usually, of course, they observe simultaneously, and that's the advantage, and that is the capability we are using to study the connection between the UV and X-rays. And okay. So, and these are the 5 different observations of this NGC 41, 50, 51. And in last 2 observations, we also utilized the UVIT gratings, while in other observations, we have only photometric data points. These are the X-ray observations. So first, we need to measure the amount of UV obscuration. So how do we measure that? So if you think of any source, then the light from such a source can be absorbed and scattered by dust grain. Particularly, I'm talking about the optical UV light. So that can be scattered or absorbed by dust grains. And this results in redder spectrum. And when this happens, when there is a loss of photons, primarily in the blue region, because the blue radiation, the blue wavelength radiation is scattered more compared to the redder part of the spectrum. So due to the effect of this scattering and absorption, the spectrum becomes redder. We call this effect as reddening or extinction. Okay, and the relative amounts of this bluer and redder light, that is essentially the color. And we measure in astronomy that particular color with this color index, so-called B minus V, where B is a blue band, which we use to measure the blue light, and V band is the visual band, which we again measure light in that some particular range of wavelengths in the visible channel. Okay, so, and these are in magnitudes, so it's an astronomy jargon, but what it means that B minus V, if this number is smaller, it means the source is bluer. Okay, and when this number is larger, the source is redder. Okay, and extinction, how much is the reddening or the extinction? That is essentially quantified in terms of the color excess. You call it EB minus V, which is the difference of this observed color index and the intrinsic color index. This we can measure by looking at the spectrum. For example, in this case, one of this AGN, when you de-redden or correct for this extinction by different amounts of this color excess value, then how this becomes bluer and bluer with overall rise in the flux as well. And this is how we try to measure the extinction. In this case, first of all, we compared our spectrum obtained with the AstroSat UVIT with the spectra, UV spectra available with the HST spectrum, because HST spectrum has much better resolution and much better signal to noise. And we find one of these spectrum actually matches very, very well. And we use this HST spectrum.
AGNs, how do you know what the intrinsic color is? Do you have something?
The intrinsic, that is what I'm coming. So intrinsic emission, what we know is primarily dominated by the accretion disk. But then in this band, there are other things like what I mentioned, broad emission lines, narrow emission lines, etc. Then there can be host galaxy contamination, all kinds of things are there. That is where the trouble comes, and one needs to account all of these various line emission components, etc. in our model. And then we try to measure this color excess by using this model. And that is where very good quality data is also required, because you have to model individual features, etc.
But regardless of the quality of data, depend on the model also, about the ability to predict what is the
Yeah, so that is partly true. But if you have really good quality data and you have ideas of what kind of model, I mean, of course, when you are deriving, it is kind of a model dependent. But these models, in the particular in the optical UV range, are pretty robust. We know there are broadline regions. We know there are continuums. But here, that is why we use an accretion disk continuum in this case. So by doing this process, what we measure is this extinction or color excess 0.38, and assuming the dust to gas ratio, what people use in our galaxy, what we will find out in our galaxy, what we find is that this kind of color excess corresponds to obscuration column of something like 10 to the power 20 or 2 times 10 to the power 21 per centimeter square from the UV ray. We can we do this exercise with X-ray data also. In X-ray, it is much, as I mentioned, it is much clearer or much easier to mention. But one has to use what is the intrinsic continuum in X-rays also. And here we utilize these complicated models. I'll not go into the details. But the intrinsic continuum, we have to use the models from other studies also, where there are better quality X-ray data also. What we infer from all these studies is that the X-ray absorption column is something like 100 times the UV obscuration column. It's a very different. Even if the dust to gas ratio is different, this kind of discrepancy cannot be accounted. So therefore, we think that the medium or which is causing the X-ray obscuration and UV obscuration is not exactly the same. How do we interpret that in result? So we know I'll come to that. This is one idea, because there are other observations which suggest that the torus, which is causing this obscuration, is not a continuous medium with the same density. There are ideas that this torus is actually consists of highly dense clouds embedded in much lower density medium. Okay, if such a thing is there, then because the UV emission, which is coming from the accretion disk, which is much more extended compared to the X-ray emitting region, which is much more compact. Okay, so because of the compactness of the X-ray emitting region, this can be obscured by smaller size clouds, like dense clouds like this. While the UV emission can actually pass through, but a good fraction of this UV emission actually can pass through through this low density medium. So in that case, because the denser objects are obscuring X-ray emitting region compared to X-ray emitting region, there the obscuration column will be much larger compared to the UV obscuration medium, which is medium between these dense blobs. And not only that, the changing look behavior now can be explained by making these dense clouds to move around. When they are moving, then sometimes they're obscuring this X-ray source, sometimes they're partially obscuring, sometimes they're not obscuring this X-ray source. And that is why the huge change in obscuration or the absorption column can cause the changing look AGN, which is essentially due to obscuration, change in the obscuration. Okay.
So what you're saying is the type 1 and type 2 are just changing in contributions depending on how these movement of these clouds are. Or
not exactly.
Okay.
Not exactly, because type 1 and type 2 is due to this one. But even if the X-ray source is obscured here,
okay,
by these dense clouds, we still have a view of the broad emission line region, which is comparable to the size of the disk.
Okay.
So those should be visible even if X-ray source is obscured.
Okay.
So this change is not due to exactly this. Okay, this is one part of the story for changing look AGN, but there are also changing look AGN which are not caused by any kind of obscuration. Okay, for example, you look at this particular AGN called Markarian 1018. In 2011, this is the X-ray spectrum observed. So you have the X-ray emission all over the soft X-rays as well as the harder band also. You go several years later, observed several years later in June 2018, the power law, broadband X-ray power law component, which is supposed to go to up to 100 kVA. So that has almost disappeared. Okay. Now the obscuration actually causes changes in the soft X-rays, not at harder X-rays. So certainly this kind of thing is not due to obscuration. In 2018, it again become very, very low, but only soft X-rays. And then when you go in 2019, then it becomes very, very strong again in both soft and hard X-rays, but the spectral shape has changed dramatically. So such changes are thought to be due to intrinsic intrinsic changes are the state changes in these AGNs. So one such AGN was we observed, it's called NGC 1566 through AstroSat. I do not, I'm actually running quite late, so I will go a little faster. So these are the AstroSat images in the X-ray and in the UV. Okay, so here we have used AstroSat as well as XMM Newton data, both in UV and X-rays for both the satellites. And again, we try to model both UV and X-rays and try to see how the various spectral components from the accretion disk, from the hot corona, etc., are actually changing when this source is evolving from from the almost quiescent level to very high flux level and then coming down. So what we observe here, so these are the spectral energy distribution derived from different observations. Two of them are AstroSat observations, and in the peak, this is XMM Newton observations, and the lowest state is also XMM Newton observation. What we see is that all these components are actually variable, but the most importantly, it is the soft X-ray excess component which varied most strongly. It varied by more than a factor of 240. It was not there in the quiescent level. It became strongest in this one. So whatever is causing this variability, that has to account this dominant variable component. So schematically, one can probably suggest that in the low flux state, the accretion disk, it was more like a standard disk, of course, truncated at some small radii. But in the high flux state, when the soft excess appears, then there is a region in the innermost disk which changed and causing the soft X-ray excess emission. And that entire thing happened on time scale of about 6 months or so. And that, how do we explain this 6 months time scale of this change? Any structural changes in the accretion disk and overall change in the accretion rate, that has to be that has to happen over viscous, so-called viscous time scale. And this time scale is very, very long, 100 to the thousands of years for this kind of AGN. So therefore there is a theoretical challenge. How do these AGNs change on much faster time scale compared to the viscous time scale? And of course, there are some ideas, but I'll not go into the details. But this is a challenge. Yes, typical alpha 0.01, in fact. Okay. The other kinds of objects are this quasi-periodic eruptions. Here, what you see is that these objects are almost quiescent, but then suddenly there is some kind of a burst which lasts for very short duration. And there's another example here you see, and these are separated with almost constant interval. It's not exactly constant, but almost constant interval. That is why they are called quasi-periodic eruptions. And when there is an eruption, the count rate or the flux can increase by orders of magnitude here. And these have been kind of a puzzle. Okay, so this is another AGN with showing similar quasi-periodic eruptions. One of the, okay, I'll skip here. There are so many models of this quasi-periodic eruptions. Some of them suggest, okay, there is some kind of stability in the accretion disk. Then there may be some interaction of the supermassive black hole with a low mass companion, which we call this extreme mass ratio in spiral. There are other ideas as well, but none of, I mean, we do not know which one of actually correct model. And in a recent observation, so with a number of satellites, including our own AstroSat, that made an important discovery, and that seems to answer the questions related to the origin of the tidal disruption events. So what are these tidal disruption events? First of all, in any galaxy, when you look at the inner regions, of course, there have to be large number of stars going around the supermassive black holes. In our own galaxy, of course, the people have resolved the stars. People actually track the orbits of individual stars, and that's how they measure the mass also. But when there are large number of stars in the central regions, and these stellar interactions can actually cause scattering of one of the stars toward the supermassive black hole. And when such a star, such an unlucky star, when comes closer to the black hole, it can come in regions very near where the tidal forces due to the supermassive black hole on the star can actually dominate the self-gravity of the star. When that happens, the star can be distorted, ripped apart, and then accretion can begin. How large is this tidal radius? One can compare tidal forces and self-gravity, and then one infers the tidal radius is something like 2024 times fossil radius for masses of 10⁶ million solar mass black holes. So because you see that the dependence of the tidal radius on the mass here. So with increasing mass, the tidal radius actually decreases. So therefore, for a black hole, for a supermassive black hole of about 10⁸ or 10⁹ solar mass, the tidal radius actually is below the event horizon. So you do not see, we cannot see the tidal disruption events for massive AGNs. Only for the low mass AGNs like 10⁶, 10⁵, 10⁷ masses, we will see these tidal disruption events. What really happens, as I mentioned, this one of this unlucky star which is scattered, this comes closer, and then it comes within this tidal radius, then stars is distorted and it's ripped off. Some part of the stellar material are actually accreted, others are thrown out, and part which is accreted that comes closer to the black hole and it forms an accretion disk like the other AGN, and then there is a huge emission. Therefore, from quiescent level, then there is a very active level and huge increase in the flux. So tidal disruption events have been discovered in different bands, in X-rays as well as in optical UV. In the X-rays, these were discovered in 1990s with the Rosette satellite, and they become very bright with a luminosity of 10⁻44 ox per second, and they come down with this prescription T⁻⁵/3, which is actually theoretically expected, which is the fallback rate of debris onto the tidal radius. Okay. If the spectrum, if you look at, they seem to be very, very consistent with the accretion disk models we already have for the AGNs. And now, of course, optical surveys, UV surveys are discovering many more such TDEs. What is important is that the optical emission is also thermal, but the radius, the sizes inferred for this optical radiation is is very large, and that is actually a problem. And the early phase emission of early phase optical emission, we do not clearly understand, in fact. Okay, but to tell you this, to continue our story, so a tidal disruption event, 2019 QIZ, was discovered in 2019 with this Zwicky transient facility. It was the nearest tidal disruption event in this galaxy, only 66 megaparsec. So an extensive study has been performed, and these are the optical light curves in different bands, and the light curves are well described by the TDE models. And what turns out that a supermassive black hole at the center of a million solar mass actually caused a tidal disruption of a one solar mass star. That is the results which came out from this 2019 event. 5 years after, when this particular object was being observed with Chandra X-ray telescope, what they noticed that they actually observed 3 times. In the first observation, this source, which is the nucleus, and this is a nearby source, nothing to do with this nucleus, actually changed its X-ray flux by almost by an order of magnitude. Okay, in the third observation, it again came down, and then The follow of X-ray studies with NICER, AstroSat, SWIFT, etc., discovered this quasi-periodic eruptions from this TDE after 5 years. And that was the discovery, because the detailed analysis of these events provided very insightful information and in the origin. First of all, if you look at this one of this eruption, this is the second eruption observed with NICER, so the count rate increasing by large factors and coming down. And when you look at the spectrum of different phases of this light curve, what you see, these are all described by the black body. The emission was very, very cool initially, somewhere here. Then the temperature increased in the maximum from 90 to about 110 electron volt or so. Then the temperature, it comes down, but the radius of the emitting region, black body emitting region, actually kept on increasing until even when this was coming down. It was like this. Only in the when it came to the quiescent, it actually appears to the black body radius appears to decrease here. And when you look at the optical UV data, particularly the late stage data when there were QPOs, the late stage data are actually very well described by accretion disk model. This is the TD light curve. The initial part is we do not understand what exactly this emission arises, what is the shape of the spectrum exactly, we don't understand. But at the later stage, obviously the accretion disk forms, and the emission is very, very consistent with accretion disk emission. Some of these points are due to the burst. So only the quiescent emission between the bursts, that is consistent with this accretion disk models. And these are the density profiles, the surface density profiles of the accretion disk. Essentially, the surface density as a function of radius, obtained from the base fitting accretion disk model, is shown here. So that after the TD event, this accretion disk form, and then because then the accretion disk also starts expanding.
Expand,
okay.
yeah, sure.
Okay, so here from the density profile, what you see is this radius is normalized by the radius where material will take the orbital period of the material, exactly the QPE, quasi-periodic events period. Okay, and this is 1 times the QPE period, and this is twice the QPE period. Okay, so it means that the size of the accretion disk is large enough to cause so that something, if it goes down, something it interacts at that radius, that can produce these eruptions. Okay. So what really is the summary? So we have a supermassive black hole, which during the TDE in 2019, it torn apart a star and formed this, started forming this accretion disk. With the time, this accretion disk gradually expanded, and it started intercepting the orbit of one of the stellar objects. It may be a main sequence star, or it may be a neutron star, or a black hole. Then this orbiting object, it passes through this disk, and the shock generated by this movement, when this passes through the disk, that can give rise to the eruptions which we observe in the quasi-periodic eruptions. So this is the overall idea of this research, which published in the Nature in very recently, 2020.
So Gulab, that has to be a compact object, right? To get the kind of luminosity you're observing. I don't think a star will do the trick for you.
A star can also, well, so what, I mean, if a star passes through this and ejects some of the material, okay, where the kinetic energy of this thing is transferred to this material being ejected, that material, that area of that material comes into picture as far as the soft X-ray emission. This is one of the possibilities.
This, right?
Yes, this comes as a black body because it is coming from the optically thick, thick material. Okay, so for example, the size of this region was of the order of solar radius, 10 to the power 11 centimeter, or twice the solar radius. That's the kind of size. So a stellar object going through is still possible, but it is not probably not a very large, massive star.
Okay, sure.
Yeah, but obviously a compact object is probably yes.
The same line. So you showed the curves of QPOs, couple of them, right? There's a weight in the repetitions. So how these weights and the repetitions of the QPOs are modeled by these companion one going to the disk?
Yeah. So first of all, if this one is a object which is moving around the supermassive black hole, it is orbiting the supermassive black hole. So if it is no disturbance, etc., of course you will expect a perfect periodicity. But there are a number of regions. First of all, it may be losing a mass. It is also possible that this disk is actually precessing. It is not more like not like a standard disk, where it is possible that if the disk is precessing, and if even the interaction between this object can transfer some of the mass or cause some of the loss of some mass from this orbiting object, and all these disturbances can produce a quasi-period rather than a perfect period. That's no. So in this case, it's a bit irregular, but in other cases, it has been found a regular pattern of increasing peak and decreasing peak. So that is actually interpreted as this object passing through the disk twice in its orbit. So that is a kind of an interpretation here. So that's where I will end. This is a summary of my talk. So I do not want to go through all this, but most importantly, this I did not cover this a lot about TDs. These objects are becoming very, very interesting. First of all, they are going to be discovered in large numbers with the future surveys in optical, ultraviolet, and in X-rays also. And they actually they will play and form an important role in understanding accretion flow and the effects of GR, because these things are occurring very close to the supermassive black hole. So, and these things are actually changing, but theoretical simulations, etc., are very, very challenging, of course. And they can actually form relativistic jets. At least there are a couple of TDEs where relativistic jets have been observed. So the formation of relativistic jet, when this TDE happens, and if you have excellent data over multi-wavelength, that is going to be very useful to study the origin of relativistic jets and the evolution of these jets. Because the TDs occur in low mass supermassive black holes below 10 to the power 8 solar mass or so. So which means one can, with having a large number of these objects, one can have a census of low mass end of the supermassive black holes. Right now, we do not even know what are the first black holes, first supermassive black holes. How do they form? What are their masses, etc.? Because these TDs can actually probe the low end of the mass. We might discover intermediate mass black holes through these TDEs, tidal dispersion events at high redshift, which future survey. There are also expected to be binary supermassive black hole. Gopu is expert on that. So this when you have a binary supermassive black holes, and in such cases, if there is a TDE, then the light curves, etc., are expected to change. So this is also a way to probe the presence of a binary supermassive black holes in galactic centers. And of course, these are very important for gravitational waves. And even in this, the current model, if this orbiting body happens to be a compact object, the neutrons are a black hole, then it will spiral in gradually, and finally it will merge. So this spiraling in, and this will obviously expected to give rise to gravitational waves. So from the gravitational waves point of view also, this kind of QP objects, as well as binary supermassive, being able to probe binary supermassive black holes with TD are going to be very, very important in future. So here I'll stop. Thank you. Thank you very much.
Thank you, Gulab. This was very fascinating, and congratulations again for the wonderful work. So,
Thank you.
questions? Yes.
Gulab, that was a wonderful.
Thank you.
But anyway, I have certain some questions. Possibly, I lost the track. See, when we go for the unification, the theory what we put for the obscuring torus is because the polarized spectrum starts showing broad emission lines. So then the idea happened is possibly most of the narrow line galaxies, the polarized spectrum showed broad emission lines. So then they found that the theory was put up is the obscuring torus is there. Possibly the hot electrons are there, which scatters off the broad emission lines which are obscured and this is scattered towards a observer's direction. So you find it in a polarized.
Yes. Yes.
So this is the one question. So what is yeah.
So this, first of all, this came after the unification scheme came, I think. So what really happens in type 2 objects, of course, in the total light, we only see the narrow emission lines. But in some of these type 2 objects, when you look at the polarized light, then this narrow emission lines, which we're seeing in total light, the polarized light actually shows a broad emission lines, actually broad emission lines, very similar to what we see in the type 1 objects.
Yes.
And that the reason is that in the perpendicular direction to perpendicular to the torus plane. So these photons actually travel, of course, because there is no obscuration medium there. So, and these travel, and there is a ionized medium.
A hot electron scatters off.
These free electrons scatter the emission from the central region, including the emission from the broad emission lines from the inner regions. And those broad emission, the photons from the broad emission lines are scattered towards the observer. Those scattered lights are actually observed in the polarized light, and we see broad emission lines.
The question is that, so when we say the changing look AGN, so the point is that when suppose it become narrow lines, still do we see in a polarized spectrum?
So the polarized light, the spectrum has been obtained for a very small number of bright AGNs.
Okay.
So these are usually at the center sites. Right now, there are no study on polarization, but that's a good way to look into this aspect.
Can I ask
the other thing, when you look at the type 2 AGNs, along with the narrow emission lines, there is always heavy obscuration in the X-ray domain. These objects, you see narrow emission lines, but no obscuration. So this is also the difference.
Can I ask one more question? Oh, yeah, sure. Thank you. One more thing I was see this changing look AGN. Okay, so what you're proposing that a clumsy the cloud model. Okay, because I got confused there also, because typically the BLR is of order of parsec scales. Okay, so what I found that changing look, the period with variation, it happens in a few years, like 2018 to 19, it's going up and down. So the parsec, is it possible, something which is at a parsec scale, to act that rapidly? So
this is the obscuration, what I'm mentioning is this is the torus. The inner region of the torus. See, if the torus is made up of dense clouds, these clouds will be moving.
Okay.
So these moving clouds can actually, okay, now there is a confusion. So these moving clouds can actually cause this change in the obscuration over, those are not that fast. And the one I discuss is that's intrinsic changes in the accretion disk.
Okay.
There are two types of changing look agent as we understand today. One is caused by changing the obscuration. The other kind of changing look agent, which we now call changing state agents, are due to the change in the central engine, accretion disk, and the hot current. There are two things.
Okay. What you showed is basically changing the accretion disk itself, central engine itself.
Yes, the later part I talked about the change in the accretion disk.
Okay. Thank you.
It's a popular.
Yes. I'll just
so Gulab, I just have a general question. So about 10% of the galaxies are supposed to be AGN. So you're not suggesting that the TDs are what is causing this activity. Clearly that won't work for more massive end of the SMBHs.
Right. TDs are short-lived objects. I mean, over 5-10 years.
So the activity, the general activity that we're talking about is probably something different.
Yes, those are the usual AGNs, which are, as I mentioned, they are almost like continuously emitting objects, not really transient AGNs.
I mean, they would, they would be active and then become inactive at some
Yeah,
now,
but that
galaxy
time
is
scale,
not.
that time scale is
Right,
very,
right.
very
So
long.
my question was, so the TD, the accretion is caused by the TDs, you said, of the order of stellar masses, maybe one solar mass or so. But in the other long-lived AGN activity case, those, what do we know what the mass of those accretion disks are?
Mass. Okay, so
Are they much more massive than the TDE disks?
yeah. They are obviously more massive than the TDE disk. TDE disks actually do not go to quite far away. They are much more confined to smaller regions. Yes.
So the TDs are not the dominant.
TDs are very small in number, first of all. Okay. So yes.
Gulab. Hi, Gulab.
Hi.
Thanks for the fantastic talk. So I'm very curious about the TDE-QP connection.
Yes.
So it's, if I understand correctly, this is a disk that came from some stripped star, asteroid star, and that
Yes.
creates a disk.
Yes.
And then some other star,
Yes.
or it can be also a compact object that is repeatedly crossing the disk.
Yes.
Okay. Yes. Twice and
Depending on the orbit, if it is highly eccentric,
And
maybe once, but
depending on the angle
yes,
of the orbit and the
that's-
disk spread,
that's,
etc.
that's right.
So has anyone tried to actually solve the Keplerian problem in the Gier limit, like trying to constrain the orbit of the thing that you do not see but may be passing through, and also depending on the magnitude and the periodicity of the disk, it can also say how warped the disk is or how
Yeah.
wide the disk is, etc.
Yeah. I mean, in this context, I think there are not much studies, but in the context of gravitational waves, particularly in the EMRI model, this extreme mass ratio in spiral, I think the people working in the gravitational wave community, that maybe people may have modeled. I think Gopu probably will be able to tell you.
Perspective, but for J287 that we model.
Yes. Mhm.
So it's but we do worry about predicting the players in advance and things like that.
Yeah.
So,
but this is interesting, very interesting idea to, yeah. So a lot
This
more
will be a
studies.
very similar calculation, and maybe.
Mhm.
Not really, the sense that I don't know if it is. Membranes are not this kind of problem. No, the tidal to TDE by supermassive. Yeah, will be a fraction of candidate. Yeah, it's a.
Yes.
No, but it's not clear for the other thing.
Yes, but we especially such installations, they don't show up with TDE. There are various calculations on that already.
Yeah.
But membranes are not going to be close. No, they are not going to be standard. So we have established a position. Yeah, hi, Gulab.
Yeah.
Very nice stuff.
Thank you.
Yes, can you look to whether you get the emission at a higher end? For example, gamma rays, MEV, hundreds of MEV.
Yeah. So what I discussed about these objects are essentially radio quiet. There is not much radio emission, but there are some observations of radio emission from TDEs also. And at least there are a couple of TDEs where people discovered relativistic jets, including one of where AstroSat contributed along with other various things. So there, the jet was pointing almost towards Earth. So the luminosity was very, very high, but for very short duration. The jet formed and then it disappeared also. There, I think even I'm not sure, but Fermi may have detected. So yes.
Gulab, it's
Yeah.
a nice discovery connecting TD and QP. Based on your perception, do you think TDs are essential for you? Or rather, every QP is preceded by a TD? What do you think?
So far, that is the indication. Not only this one, of course, is very clear, but there are also study of for example, there are QPE sources, which are what kind of AGNs or hosts are those objects. And in the first two QPE sources, including one we studied during my PhD also. That time, what we obtained is the host galaxy type and the AGN flux. And in some of these QP sources, what people have seen that X-ray flux actually has gone down. The quiescent level flux has gone down, very similar to the TD. So now people, after this thing, people are now assuming most of these QPs are due to TD effects. TD is so far it looks like the case, but we will wait because there are other models which can also result. We'll have to see those things.
Goku, last question.
Yeah. So this is about that clumpy torus you talked about.
Yes.
But you need to worry about the gravitational stability of that such things, right? When you bring in the clumpiness and all that, and try to fit in that create instabilities and all that thing. So people are worried about that, or
yeah, that's a good question. And this clumpy torus model came very recently, and this entire thing Jai was mentioning was introduced to unify different things. And some recent high resolution observations in the infrared do not exactly show like this kind of a torus structure, but some kind of a infrared emitting object is there, because these are supposed to be, but they are. It's very difficult to say they are actually in the torus kind of geometry, but there is some structure. So I myself do not work directly on this torus, but I think the people have studied the stability, or people are studying stability, etc., and it is possible to have. Of course, see, there are much more complex than we think. There are winds also, and these torus are actually they're also supposed to give rise to some kind of winds. There is a heating from the central source. One has to take account of all of this, and yeah. So the full detailed study probably is not there, but to some extent people have investigated.
So that's just a follow-up of JWST. Some of the nearby ones should be kind of.
Yes. That's very, very important indeed.
Okay. Thanks.
Yes.
Thank you. Thank you, Gulab. That was fantastic.
Thank you.
Thank you for coming and sharing this exciting science. I welcome all of you to join for some snacks outside the West Canteen. So thank you very much. Thank you to everybody in the AV team for helping us again this week.